Okay. Okay. Yes, better. Good. Okay. So thanks again. Okay. So what we did yesterday for the we needed for today's lecture was computing a path integral for two large charge operators in a specific theory, in a weakly coupled theory, and we found that rather intuitively. So the idea today will be to generalize this lesson and try to use effective field theory more in general without assuming weak coupling in the theory. So the setup, just remind you the setup, also for those who were not here yesterday, it's a CFT in dimensions larger than 2 with an internal symmetry G. You call QIs the global cartons of the symmetry group, so the highest weight, so if you focus on highest weights, of course, they label the representation of all the operators. And you can include spin in the game, angular momentum. And you call the lightest operator at fixed charges, you would just call it OQ. Okay? So the idea is just like, say you want to compute some correlation function, the simplest is the two-point function. This, by state operator correspondence, maps to a correlation function on the cylinder. So an time evolution operation on the cylinder between two states of charge Q. And this admits a path integral representation, at least intuitively. And I just remind you that the Hamiltonian of the cylinder is given by the dilation operator divided by the radius of the cylinder. And of course, what we want to assume now, based on yesterday's lecture, is that for large charge, you expect a classical trajectory to dominate this path integral. So, why this is a useful assumption? It's a useful assumption because a classical trajectory is essentially, by definition, non-trivial. So it transforms non-trivially under the symmetry group of the theory. So the symmetry group is the conformal symmetry group and the internal symmetry group. So, okay, so let me just maybe put them here for a moment. So, what happens to the symmetry group? So let's look first at translations. So translations shift the insertion point of the first operator. So imagine putting the two operators very far apart, one at the origin, one say at infinity. Translations unavoidably shift the location of the first operator. So this means that the saddle point cannot be invariant under translations. So these are the flat space translations. So they are broken. For specular reason, special conformal transformations are also broken because they shift the location of the insertion at infinity. Okay, so please interrupt if there are questions. Okay, so so rotations is in general harder to decide, but now you can make an assumption. So here we will make the hypothesis, and we will partially lift at some point, that the state we are considering doesn't have spin, and therefore you expect the saddle point to be homogeneous. In fact, I think it should be. So we can assume rotations to be preserved. So maybe just a word of caution for those who were not here yesterday. When I speak of spontaneous symmetry breaking, it's only at the level of the saddle point. There is no spontaneous symmetry breaking on the at finite volume on the sphere. So this means that the path integral will have zero modes that restore the symmetry. Okay. So the interesting question concerned the Hamiltonian or the dilation operator in the internal symmetry. So here there are a priori two options. You could have that both D and G are preserved. So let's think for a moment about this option. So this somehow seems the simplest one. It just means that the classical trajectory is stationary physically. Is static, not stationary, sorry. But okay, this means that in this, when we will go to construct the Goldstone bosons associated with the classical trajectory, so the effective field theory, we will not have any degree of freedom that carries information about the internal symmetry group. So we will need somehow a way to represent a finite charge density without Goldstone boson in the theory that can do it. So the only effective field theory that, well, you can maybe try to construct effective field theories of this sort, but they typically run into subtleties for situations where you don't have large degeneracy. So like one example is hydrodynamics, but hydrodynamics really works at finite temperature. Here we are not at finite temperature. So in this setup, I expect that generically that this setup cannot be associated to semi-classics. Fortunately, it's not a theorem. But yeah, so the examples that we know so far is that if this is the case, in fact, there is no classical trajectory in the path integral. The other option is that this gets broken to a linear combination of the Hamiltonian and the internal charges and the internal cartons, and maybe a subgroup G tilde of G. So let me just write it like this. Okay. So this option is what defines the generalized superfluid. And this option is quite natural because since you will break in partially the internal symmetry group, now you have Goldstone bosons that can realize the charges, and therefore you can realize your classical trajectory in the path integral. So this is generalized superfluid. And this is the one we found was the right answer yesterday. Superfluid. Okay.
Gabriel, can you explain better this implication? You say we have Goldstone bosons and therefore we can realize classical trajectory. What's this?
So I mean, so look, I'm just saying if you don't have if the internal symmetry if the internal symmetry group is not broken, so now it means how do you realize the charged operator? You cannot write it in terms of Goldstone bosons in the effective field theory. So it means something else should be a charge operator, and this something else shouldn't break the symmetry. So as far as I understand, there is no way to make it semi-classical. So you still, a priori, you don't need to realize charge operators in your theory. It may be that they are not, like baryon number. You don't have any low energy operator in QCD that realizes that it's charged on the baryon number, but you want to realize the charge because the charge you are at finite charge density. So you need some classical operator made of Goldstone bosons that realizes your charge density. So you can imagine that this happens through some topological charge or in hydrodynamics, but as far as I understand, none of these examples typically are. I think it's not a theorem. It's just that I don't think we know ways to realize this scenario consistently. So you should have a charge density, but it shouldn't be a composite of any charge operator that you can realize in your effective field theory. At zero temperature, I don't think we have many examples where we know how to make this work. It's just our lack of fantasy. It's not. But okay, if you don't assume semi-classics, like Fermi liquids precisely realize these options. So this is just in the assumption of semi-classics. You can have a.
Yeah, can you repeat the question?
So you're asking whether the subgroup preserved here. Yeah. So the generators here need to commute with the unbroken Hamiltonian. Was this the question? Yes. Yeah, so this will be important in a moment. Okay, so let's summarize. Okay, so within the setup of the assumption for today, we will try to lift some of them tomorrow. Our symmetry group, our symmetry breaking pattern is of this sort. SOD times H bar H minus mu I QI times G tilde. So this is our symmetry breaking pattern. So what are the modes that describe the symmetry breaking pattern? So of course we have the Goldstones. And the Goldstone modes actually turns out, even though you're breaking some space-time symmetries, are only the one associated with internal symmetry breaking. So I'll review the Goldstone theorem for this setup in a moment. And a subtlety here that not all of you might be familiar with is that Goldstone theorem must be thought as the Goldstone theorem at finite density. So it's not the relativistic one that you know, even though some implications are clearly similar. Okay, so what other modes can there be in our theory? So in the simplest assumption, all the other modes should be gapped. at a scale roughly set by the charge density. Okay, so let me just write generically. Gap at the scale set by the charge density. So the scale of the mass just follows by dimensional analysis. Some intuition for this is the following. So you can think as turning on a charge density as somewhat equivalent as turning on a chemical potential. And a chemical potential is a relevant generic deformation of your Hamiltonian. So what happens when you turn on a generic deformation? You should flow to a simple phase. So like if you turn on a mass in a QFT, you generically go either to a gapped phase or to a symmetry breaking phase, unless you tune to a special point if you have some parameter to tune. So here, if you turn on a generic direction, the chemical potential space, you should flow to a simple phase. Since you're breaking some symmetries, this phase cannot be gapped, but you shouldn't have extra mode accidentally. Of course, if you have more than one chemical potential, then you will have some dimensionless ratio that you can tune, and there might be phase transition at those points. But beyond those points, you should expect modes to be either gapped or Goldstone bosons. Okay, so this is... And of course, this means that you have effective field theory in a derivative expansion, roughly. Mu to the 2n. And if you use the derivative as roughly 1 over the radius of a cylinder, this is 1 q to the 2n d minus 1. So the derivative expansion turns on in expansion in powers of the charges if you relate the chemical potential with the charge density by dimensional analysis. Okay, so in the interest of being, so this is started. So Goldstone theorem at finite mu. Theorem. Okay, so let me just highlight two differences between the Goldstone theorem at finite chemical potential, the Goldstone theorem that you all know, that so that you understand that it's understand how to extract this effective field theory. And the main difference is that now the unbroken Hamiltonian is actually, since there is no boost at finite density, it's a linear combination of the original Hamiltonian and these charges. So therefore, generators can be divided into two classes. Those that commute with the charge that appears in the unbroken Hamiltonian. And this leads to a number of massless Goldstone, which is between the number of broken generators divided by 2 and the number of broken generators. So I think for today's lecture, this weird fact that the number of Goldstone bosons may not coincide with the number of broken generators will never appear.
So what's NA?
So NA is the number of charges QA that commute with the mu IQI, the charge that appears in the unbroken Hamiltonian.
And so why do they call them broken generators?
Spontaneously broken, I mean. So I'm just saying, the spontaneously broken generators, you can divide them into two classes. Sorry, I wasn't very clear. Let me repeat again. The spontaneously broken generators can be divided into two classes. The first class is those spontaneously broken generators that commute with the unbroken Hamiltonian. So given the number Na of this, there are in between Na and the Na-half massless Goldstone bosons, and there are counting groups. It's strict. It's like this. It's not strict. So today, the example of today will always be essentially, well, not really. Yeah, I think they will always be essentially an A. But we know how to count them, so it's systematics. So it just gets a bit technical. So then you have the spontaneously broken generators that do not commute with the unbroken Hamiltonian. So there is some confusion in the literature on this point, because sometimes people say the chemical potential is an explicit breaking, but from my viewpoint, I'm just saying I'm picking a state with finite charge density, but the symmetries of the system are the same. So the chemical potential cannot be an explicit breaking. But there is some truth to this statement, of course, and the point is that the generators that do not commute with the Cartan here that appears in the unbroken Hamiltonian can always be divided into pairs, just because it's a non-abelian group. And these pairs will form sort of ladder operators, which have commutation relations of this sort. So these are like lower raising operators. And then we'll have plus minus mu, some QA. Let's just write it like this. QA plus minus. So mu, if you want, is roughly the model of this mu I. But that's just really the right-hand side is the definition of mu QA. And okay, now you have broken generators which do not.
Sorry, since you never say you're always right, but you don't pronounce. Can you say mu1 Q1? What's mu1?
So these are some linear combination of the Cartan generators.
So it's not 1?
Well, you can always write this as, you can always define this to be mu q.
Yeah.
So I just, but typically, so the reason why I write it like this is that typically given a symmetry group, we choose our, like say SU3, you choose two Cartan generators which label your representation in a natural way, and you don't want to keep track.
It's just I don't understand the indexes. Is it a letter?
I.
Or is it a number?
No, it's I.
It's I.
Sorry,
okay,
sorry.
Good. Okay.
Sorry. Yeah, my bad. Thanks. So anyhow, the bottom line is that the spontaneously broken generators do lead to a prediction, but it's a somewhat weird prediction that you have Goldstone bosons which are gapped. You can predict exactly their gap. And kind of makes sense because acting with this Goldstone boson on the vacuum, okay, that doesn't really make sense spontaneously breaking to act with a broken generator on the vacuum, but if you do it and commute it with the unbroken Hamiltonian, you find this result. But anyhow, it's a theorem. So I'm not giving references because in the references I gave yesterday there are precise references for all these statements. And there is one gapped Goldstone for each pair of non-commuting generators. So also this is another difference. So it's not one per generator, it's one per pair. That's the theorem. So let me just run two examples. Okay, the one example is the case of a U1 symmetry. You have the Hamiltonian, you have the U1 charge, and then you break them to H minus mu Q. This is what we discussed yesterday. You have one massless Goldstone only. The next two simplest example is SU2. You have H, and you have the three generators of SU2. So there, you will break it now at finite chemical potential to H minus mu Q3, and that's it, because nor Q1 nor Q2 can commute with this. And therefore you get one massless Goldstone boson plus one gapped Goldstone. Okay. And the gap of this Goldstone is mu. So in some sense, typically the reason why people say that the chemical...
Are you going to derive this?
No.
But can you give some intuition why, for example, why is there between 1/2 and one massless? Between this equation NA over 2 and A,
okay,
is there
so
some intuition?
the intuition of why you can get a half here is that, so these are pairs, okay, so for each pair, there is one single gapped Goldstone. And the idea is that one of them will kind of annihilate your vacuum and the other one will create the gapped Goldstone. Now imagine you have several chemical potential. You can tune to a point where this right-hand side becomes 0. This means the gapped Goldstone become massless, but you still have only one for each pair. So that's why sometimes for each pair you can get only one Goldstone boson. So that's actually the intuition of how this happens. And this also tells you something, was the gapped Goldstone dispersion relation is naturally quadratic. It's mass plus k squared over m. So this actually, to get this a half, is crucial to have Goldstones which have the dispersion relation, which is omega equal k squared rather than omega equal k. So there is actually also this can be made sharper.
But I guess the kind of question that I was wondering, to prove the Goldstone theorem, you can prove it, but you can just write down some effective Lagrangian from which you see the number of Goldstones very clearly. So here, is there some similar effective Lagrangians that you can write which would demonstrate these statements that you made?
Yes. So I mean, so the point is that you're breaking spontaneously boost. So sometimes the leading order time derivative terms for Goldstone boson can be one derivative. So once you break out boost, your Lagrangian for the Goldstone bosons will be something like p dot I, p dot j, this states are your Goldstone boson, some metric Gaj. Then you have an antisymmetric tensor, pi, p dot j, and then you have the kinetic terms. Let's say if we're diagonalize this, and that's it. Now, now a single time derivative kinetic term can actually lead to quadratic dispersion relations, and the extra complication is that some of them are expanded around this kind of background, plus delta pi. So now one can work it out from here, of course. But now has to understand constraints on this, the counting rules. It's a straightforward, but it's yeah. I think it would take us a bit far away in these lectures. But yeah, you can do it. But okay, yeah. Okay, so let me start from the simplest effective field theory.
Sorry, the gap of the gap Goldstone is of the same order as the gap of the radial modes, or there is a hierarchy?
It's of the same order. So we will discuss for a moment if these are... Yeah, so roughly speaking, people in the literature forget about gap Goldstone for this reason. It's not entirely correct. I'll comment about it, but...
So okay, you'll tell us in a minute, but are you going to include them in the effective field theory or not?
No, okay, so I will never write any effective field theory with the gap Goldstone because there are all tons of subtleties in doing that. But I'll tell you, I can anticipate it. So roughly... Okay, let's wait 10 minutes because, I will not include it, but I'll say something. Thanks. Okay, so the U1 superfluid, U1. Okay, so let's start from the simplest one. So in this case, we have only one Goldstone boson, and we can always write it as we did yesterday, as some phase. You expand it around the background in Euclidean, and then the fluctuation. And this background precisely realizes the symmetry breaking pattern I said. So to write the action is straightforward, but let me just give you the trick, so for those who never thought about it. So you want to write an action which realizes U1 symmetry and conformal symmetry, but it's actually simpler to realize while, as typically in this happens, and this always implies conformal symmetry. I don't know if this example you can write terms which are conformal but not while invariant. Anyhow, you expect while. So to do this, you have to write building blocks which are both U1 and while invariant. U1 is a shift of chi, while is a rescaling of the metric. So you define a hatted metric like this. D mu chi, absolute value. So I write an absolute value. It may not look very analytic, but I'm expanding around the background, so it's analytic in pi. So you can check that this is actually while invariant, this combination. And the other while invariant combination is just derivative of chi. It doesn't have any metric, so it's while invariant. So then the action is written a derivative expansion. The leading term is just the cosmological constant term for this hatted metric, square root of g hat. And this is minus C1 integral d dx d chi to the d, where d chi to the d, so this is just d chi square in my notation, once for all. And this scales like mu to the d. The subleading order terms are just, it's very simple again. It's ddx square root of g hat c2 r hat plus so you see, in terms of this hat metric, I just need to write essentially diff invariant stuff, which is trivial, and contract it with this vector, which is kind of my breaking of boost. And then I just need to expand this again into fields if I want to write something which is useful. But okay, and this you can just look at your formulas for while rescalings in World Book or whatever. C2R plus, so there are completions. D mu chi, I think. D chi square, I think. Plus completion. So the dot 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 stands for terms with more derivatives on chi that you can construct again just by expanding those terms. And this scale like mu d minus 2. And you can go on, and in even dimension, you have also West zoom in term, because you have a conformal anomaly and you need to match it. And also these are written, so West zoom in term are typically written in terms of the dilaton, but here you see that this d chi square has the same role of a dilaton, so you can write them in terms of this d chi square. They work in the same way. But those are typically quite subleading. They scale like mu to the 0. Okay, I'll let you solve this for a moment. Okay, so you have an action, and now you can do some calculations. So these are analogous to the one of yesterday, so let's be quick. So from the saddle point, you learn the ground state energy. So it's just proportional to the path integral, e to the minus the action. But then you have to include some wave function s to fix the charge at initial and final time. I think we discussed them yesterday. I'm not entirely sure. If not, the role in life of these guys is just to fix the boundary conditions. These are analogous to like wave functions e to the im phi in quantum mechanics. So like just there is a smearing over the sphere. So this fixes the charge, as we are saying. And okay, so the solution, this background is always a solution of these equations, just because we act twice with derivatives on chi, so it's trivial to see. But then you have to fix mu, and mu is fixed by the boundary condition imposed by these guys, and then a straightforward calculations tells you that mu is precisely what you expect. Is q divided some factors, where omega is the volume of the sphere for me, 1 over d minus 1, plus corrections in 1 over q. So this is what you is the relation between mu and the charge density that you expect on dimensional analysis. 1 over q2 over d minus 2, d minus 1. So notice yesterday we had the same thing, but here there was an epsilon. And the point is that in this Wilson coefficient, so C1, C2, C3, we typically take them to be order 1 in strongly coupled theory, but they should generically be large in weakly coupled theory. So they should be like 1 over lambda, something like that, where lambda is your weak coupling. So in that case, you can accommodate that case, of course, but typically the large charge, as we saw yesterday, means parametrically larger than the coupling. Okay, so, and okay, here it's just nice straightforward to derive the formula we had yesterday. Plus alpha 2, qd minus 2d minus 1, plus alpha 3. So I'll just go to this order. Okay, you understand how it's going. And okay, and you can also give an expression for this alpha 1 in terms of C1, and alpha 2 in terms of C2 and C3, and so forth, so on. And here there is also, here is only a classical level. There is a one loop contribution that I'll discuss in a moment. Okay. So maybe one comment about this formula. I think you've seen it already. But so the leading term here, we already argued yesterday, just dimensional analysis, a relation between energy density and charge density. What comes from effective field theory is that this form really takes the form of a 1 over mass expansion, so 1 over charge density to the appropriate power. So this is the non-trivial input effective field theory, which is encoded in the fact that I'm only writing analytic terms in the curvature here. So this is what effective field theory is buying you. But okay, that's just one formula. Effective field theory, of course, buys you more. Okay. Good. You have fluctuations. So to see that, let's go to fluctuations, the action for the fluctuations to quadratic order. Okay. Turns out to be very simple. Well, it's not you could have had much. Okay. Okay, so this is just relativistic action with a weird sound speed, and therefore you conclude that your spectrum is given by Fock modes with this dispersion relation plus correction, which are suppressed in the chemical potential. And this JL is L, is just the eigenvalue of the Laplacian on the sphere. Okay, so 2 comments. Okay, so these Fock modes create states and therefore create the other operators with scaling dimension you can predict. So one comment is that the L equal 1 state has precisely energy 1 over R. And this is because this creates descendants. We know it should be there. We know that descendants should be there just because the theory is conformal. And in fact, the fact that we wrote an action which was properly conformal ensured that the sound speed here was right to get this. Okay? And another stupid. So the other comment is, of course, this expression immediately gives you to compute the one loop. Correction to the formula before. It's just the Casimir energy of this guy, so it's a sum of 0-point energies. And okay, so here the results depends between d equal 3 and d equal 4, and or the number of dimension in general. So in d equal 3 turns out to be a number. And the reason why it's a number, once you properly regulate this sum, is that in this expansion there, that goes like in d equal 3. Okay, let me just write this. This is alpha 1 q to the 3 half plus alpha 2 q to the 1 half plus q to the minus 1 half. So there is nothing which scales like q to the 0, and the Casimir energy goes like q to the 0. So nothing can renormalize the Casimir energy, so it should be finite. D equal 4, the story is different. The leading order is q4 third, q2 third, and the subleading order is q to the 0 indeed. So this means that the Casimir energy can be renormalized by this coefficient alpha 3 here. So whenever you have a situation where a quantum effect can be renormalized, you know you should expect a logarithmic divergence. And our cutoff is parametrically given by Q. And you can predict a logarithm of the cutoff. So, and turns out that in this case, the universal part of the Casimir energy gives you this answer, gives a prediction for a log of Q term. Right, yeah, so you can, I'm not discussing how to do that. You can do it, like one way to do it straightforwardly, I wrote the action in d dimension, so you can just work in d dimension, we are in DIMRAG. The multiplicities of this Laplacian will regularize your sum in DIMRAG. So, yeah, but you need to regularize it in a way which is compatible with the symmetry. So that's the only subtlety of the calculation.
I'm sorry, when you read d equal 4, you mean really d equal 4 minus epsilon?
I really mean d equal 4.
But in d equal 4, there's...
well, you can maybe
why do we care about d equal 4?
Is there some, maybe there...
Well, yesterday we discussed, for example, d equal 4 minus epsilon, which is...
I mean, I'm just saying. So they assume some CFT in the dimension with a U1 symmetry. Then you might say there is maybe d equal 4. It's not interesting to study, but I can do the effective field theory construction anyhow.
Okay, maybe I should then ask what's going to happen in d equal 4 minus epsilon.
Well, in d equal 4 minus epsilon, this log. So you should expand those powers of d in 4 minus epsilon. You will get logs out of those power, and that's somehow you can get convinced that this log fits into this scheme. I don't know, should I go more details? But in 4 minus epsilon, like we had logs in the calculation that I discussed yesterday, well, not Diego, and the interpretation that was they were coming from those power. So somehow, yeah, so you have this log, and you write it as log minus constant plus constant. Log minus constant fit into the expansion, and plus constant because they Casimir energy, which is finite away from the equal 4. That's essentially. But okay. But okay, I think the point of effective field theory is, okay, I agree. D equal 3 is the case, which is interesting for, at least for this class of EFTs. D equal 4 maybe theories with moduli or something else. Okay. Okay, so assume many of you seen this, but if not, please ask question, or even if yes.
Sorry, an elementary confusion. There's no constant term in d equal to 3, but you have a constant here.
So yes, so in d equal 3, you should add the one. There is the one loop term, which I should have written. So there is this one loop. So this is this constant term. This is the classical piece. This is the one loop. And in d equal 3, so this gives you actually a piece standing here. This minus 0.09.
Thank you.
Yes, thanks. Right. Okay, so we computed something small. Good. Okay, so let's go to the non-abelian case, which will be slightly less discussed and sometimes slightly more confusing. Other symmetry groups. Symmetry groups. And from now on, I'll set d equal 3, so Slav is happy. No, I mean, I was planning to do it anyhow. So I'll take G. Okay, SU2. We kind of discussed already before what is the spectrum. You have an effective Hamiltonian, which is H minus mu Q3. So you have one gapless Goldstone and one gap Goldstone. So this means G fully broken. Okay, so if you neglect the gapped Goldstones, you have the same story of the U1 case. So this means the light states goes as before. Now, of course, and what does the saddle point in the potential describe for you? It describes the highest weight state in a certain SU2 representation. Now, if you have an highest weight state, you should have the full representation. And it turns out that to reconstruct the full representation, it's enough to include the zero mode of the gapped Goldstone. So you will imagine including an extra field in your Lagrangian, which is gapped. You will have a number of angular momentum modes, L equal 1, 0 equal 1, blah, 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 blah. Now, the L equal 0 mode, as it is typical in the case of Goldstones, is actually protected, and it creates the other states in the representation. So reconstructs the SU2 representation. So you might say, this state, why is it gapped if these states are degenerate? Well, there is a small subtlety whether you measure energy with respect to H minus mu Q3 or H. So that's kind of why this question about the gap may be confusing. But for the zero mode, effectively, it does what you expect. Actually, the higher mode turns out instead. So somehow the zero mode, if you want, is charged under Q3. That's why the gap, you don't see it. The higher modes instead are not protected. So they mix with all the other states at the same energy. So what's the picture that you should have in mind here? So you have this gapped Goldstone. For a moment, let's take an infinite volume limit. The field is the same. And imagine you have your gapped Goldstone traveling in your theory with some momentum non-zero. Now, nothing prevents this gapped Goldstone to decay in all the other, in whatever other energy state which is degenerate with it at this state. So there is no boost. So as long as k is non-zero, this can decay. For instance, it can decay into n many massless Goldstones. And the problem is that we do not control all these states in effective field theory. So this mixing process is not under control. So, of course, for the infinite volume perspective, this means the gap Goldstone is a resonance. At finite volume, decay, so means that pi plus is not an eigenstate of the Hamiltonian, and therefore we cannot predict its energy. So this is the subtlety with including gap Goldstone in effective field theory, and for the sake of the spectrum, the generic answer is that you can forget about them for this.
I'm sorry, did you explain why the zero mode doesn't suffer from the same problem?
Well, so what does Goldstone theorem guarantees you in the non-relativistic case? It only guarantees you the existence of zero momentum excitation. That's because you don't have boost. Relativistic Goldstone theorem, if you want, does the same, but then you boost your excitation and you have them at any momentum. In the non-relativistic case, the same is not true. So the non-relativistic Goldstone theorem guarantees you this excitation exists, and therefore you can describe it, but doesn't really tell you much about this. Of course, by continuity, you can expect this process to happen very slowly, but this is even more subtle how to interpret this in effective field theory, and I will not do it today. Does this answer your question?
It's just from what you're saying, why do people talk about this gapped Goldstones if they are totally useless for any practical purposes?
No, they're not totally useless. I mean, because okay, so imagine that you know, okay.
Do they exist as particles, as excitation?
I mean, the width of the gapped Goldstone goes like k square over the gap, so it's low in the limit of k.
Okay.
So in this sense, you can talk about them, but then to interpret this in CFT, you have to go to some correlator and it gets subtle.
Okay.
So I wasn't planning to do that. Yeah, thanks. Okay, so but they're actually also sometimes useful in CFT because there is of course an obvious exception, which is when the gapped Goldstone is charged under a discrete symmetry. Let's say under a Z2 or other discrete symmetry. And the reason why I'm mentioning this is that this is what happened precisely in the O3 model in 3D. Well, we know that this happened in the epsilon expansion and kind of completion, so if you assume the same quantum numbers. So this actually tells you that you can now trust your gapped Goldstone state is your theory. And the first charge state, which is Z2 odd, is actually gapped with respect to this first charge state, which is Z2 even. And you can predict the gap. It's just R mu, which of course just d dq. And in fact, if you're careful, there is also the kinetic energy of the gapped Goldstone, which goes like this. And this also means that the angular momentum of these states is non-zero. And this kind of matches what you expect from the exponential expansion for those of you who are practitioners, because to build a Z2 odd state, you need to use an epsilon Levi-Civita tensor. And to do that, you need to input some derivatives. Otherwise, you just vanish identically. There is no way with a single field to build a Z2 odd state. And this is actually reflected in this formula in the fact that actually, even at large charge, this state typically carries some angular momentum. Of course, you can also make one with zero angular momentum, but you have to combine it with the gapless Goldstone states.
So this is what? This is this the global Z2 or the spatial Z2?
Global. Global. So the O3, I'm just saying O3 is SO3 times Z2, something like this. Maybe semi-direct. So I'm using this Z2. Okay, so I'm not doing with time because I don't want to spend too much time on abelian symmetries. Oh, 10:15, so start 9:30. Okay. Okay, so yeah, okay. Just for completeness, let me discuss a bit more on abelian symmetries, and then maybe we'll go to something more fun.
Yeah, just in case it's useful, there is a clock there.
Ah?
If it's useful for you, there is a clock there on top.
Ah, okay, good. Thanks. Sorry. Okay. Okay, so the last example, let's take a rank 2 group, and the simplest rank 2 group is U1 times U1. So you might say, U1 times U1 is not a very interesting group, but actually the point is that once you go to the generic saddle point, which will have two chemical potential turned on, in this case, the generic, even if this was, say, an SU3 group, and these were the two cartons, Q3 and Q8, this would fully break the group, and if you forget about the gapped Goldstones, as I was explaining before, essentially the situation reduces to the U1 times U1. So you have two Goldstones, K1 minus I, K2 minus I mu 2 tau, plus pi 2 of x. And yeah, so the only thing which is interesting here is that now the effective field theory is not fully fixed even at leading ordering derivatives. It's just something like this. What is this going on? Pxy. dk8, dk3. Okay, so the only reason why I want to discuss the case with more than one symmetry is that I told you before, when you have two chemical potential, you can expect something interesting to happen. And in the effective field theory, this is reflecting the fact that now the leading order action depends on a generic function P. So this is not a big problem to deal with, because now you're expanding. But the point is that now this action may have singularities. And singularities, as well known for EFT practitioners, are just points where light degrees of freedom come down. So new light degrees of freedom. So you see in effective field theory now, having large charge is not enough. You also have to assume that you're expanding around a point where this P is regular. And this means also that if you travel in the space of this, sorry, this is 1 and 2. I don't know why I read 3 and 8. I had in mind SU3, sorry. 1, 2, 1, 2. So this means that this actually, the reason why this case could be interesting if one has a model is that if you now travel in the space of the charge density or in the space of the chemical potentials equivalently, you might reach points where there are interesting phase transitions. But the rest of the story is pretty much the same. Delta goes like some function of Q1 over Q2 times Q1, Q2 to 3 plus corrections, 3/4, sorry, now, because the overall power. And alpha now is some function of the ratio of Q1 and Q2 that depends on P. You have two excitation. One of them has the same dispersion relation as before. It's LL plus 1 divided square root of 2. And again, you must have this one because you must have a descendant. And then the other one is actually as a sound speed that you cannot fix. You can only in effective field theory. So the only thing you know about C minus is that it's between 1 and 0. So, but otherwise, the story goes pretty much the same. Mm-hmm.
So, singularities in EFX line,
I mean,
Repeat the question.
okay, let me see. So he's asking how to think of these singularities, if you should think of them as singularities in the ratio of the charges or something. I don't know what's that. So, you're now going to expand this guy around the background. So, X, so you're now going to expand in pi 1 and pi 2. Okay? So to make calculation effective field theory, expand in this pi 1 and pi 2. And to expand, you have to assume that derivatives of P are regular, are finite there, right? And
Right.
So, so this singularity, so the meaning, so this means you're expanding, this means that, for instance, x is, I think, is actually, the background is actually 1, but y, the background is mu1 over mu2. This means that as a function of mu1 over mu2, there may be points where these derivatives become huge, and the derivative expansion break down, so such that so the expansion implies equivalent expansion derivatives of these functions essentially, and if they become too large, the effective field theory breaks down. So you should think of them as you have a dimensionless parameter, indeed the ratio of the chemical potential, and then you tune, and scanning this parameter, you can encounter some interesting points.
So in other words, all that's happening is that I have a dimensionless parameter, and my Wilson coefficients are functions of this dimensional parameter.
Right.
And they can have singularities.
Yes, it's like lambda phi 4 theory. You have a lambda over m, which is your dimensionless parameter in the equal free, and you find a phase transition at some point.
Okay, thanks.
So yeah, so this is the only, again, I stress in the case of U1, this freedom is not there once you assume a superfluid effective field theory. Okay, so let me discuss something maybe slightly more fun.
So these coefficients of this P, does it depend on, can it depend, for example, on mu1 and mu2?
It depends through this x and y. So that was fast, sorry, I should have spent more time here.
Only through x, so it has, otherwise it has no dependence on mu1.
No. So I'm writing, so exactly, so P is just a function, and the chemical potential enters through the expectation value of this K1 and K2. So, and again, this is because the reason why this is like that is because of Weil and U1 invariance. So P, I cannot put functions of, I cannot mu by hand somehow. It's just the state of spontaneous breaking. I don't know if I'm explaining well, but I'm just saying the depends on mu1 over mu2 is captured purely by this function y.
But is it like an arbitrary function? Because if you move to another, why should there exist a unique function p of xy which covers all possible cases?
No, it's not unique. It's p is an arbitrary function which is theory dependent.
Yeah, but for example, when I change mu1 and mu2, how can you argue that the function p remains the same?
I mean, you're wondering if so the effective field theory can only depend on dimensional ratios mu1 and mu2. And this is a situation which realizes this. And so I'm just trying to understand what's the question. So you're wondering.
Like, can you give some example of a function p? Maybe that would be a good thing.
I mean, it's an example. Well, any example. Say, I don't know. So I don't have it in top of mind an explicit example. You could take a power. For instance, this would be maybe regular.
Okay.
You can take whatever function. You expect it to be smooth at a generic point. Notice, okay, another example is the relativistic superfluid without conformal invariance. Also depends on a function of this decay. People computed recently at one loop in some simple lambda phi 4 model, and it's some complicated hypergeometric. You don't expect any simplicity in this function, but you expect that a generic point will be smooth unless something is happening. It's like the effective field theory for moduli spaces in superconformal.
But so you talked about, so when you talk singularities of the function, you mean?
The derivatives become huge.
But the function itself, you think, remains smooth, or what? Because one could also imagine that
the function can go to infinity.
There could be phase transitions associated with passage of one function p to some other function
so
p
the
tilde.
physical, okay, let me give the physical meaning of this thing here is the pressure of the fluid, and then whether it's the pressure itself, the first derivative, or the second derivative, which is discontinuous, depends on the order of the transition. So it's precisely, I mean, I don't know. I don't know to say something general. It's a theory-dependent question, where the discontinuity appears.
Can I write, for example, p of xy equals absolute value of x?
Yes, any function of x and
Any
y.
function, okay. But then it's going to give rise to different singularities.
Yes.
Okay.
Yeah, so I'm not saying that I know which singularity. I'm not saying that the singularity will always be second order phase transition, if this was the question. I have no idea. It could be first order, it could be model dependent. Why? So why is that? What idea? So like y 1 minus y. I think so, and this could be, and this would be a singularity when mu1 and mu2 become equal. This could totally happen, yes. Yeah, I mean, I think any function which smooths at generic points and has some finite number of singularities should be okay. If it's singular everywhere, of course, you just don't have effective field theory. So, well, I mean, there are some positivities on the derivative which come from the constraint that this sound speed, which is a function of the derivatives, should be subluminal. And you can also imagine more positivity properties of this sort, but they are typically not very intuitive to write down in terms of P. Yes? It could be that one. So okay, so the question is whether there could be symmetry enhancement at these points. So it could be one way in which it could happen that you have a transition is that one of the two broken U1s gets restored at that point, and the radial mode also becomes light, say in a weakly coupled model. That's a totally, maybe that's the simplest example to imagine. Yes, so that's, yeah, I agree. That's a natural way. So you have the, when the generator. But yeah. Yeah, I mean, you can, so then it's an all interesting question, but the point is trying to find an example where you can know this P and you can find these points. The generic point is the story. Okay, so I think, yeah, okay.
Sorry. So there's one, there could be one interesting candidate theory to study in the scenario, which could be the two Fourier QD3, and the global symmetry is the SU2 cos U1, and then the Cartan subalgebra of the SU2 is another U1, so you have the two U1 cos U1 like you write down here, and then it's possible to compute the effective field theory of the theory and then check if you can find the singularities and then what happens at the singularity point.
Okay.
Yeah, that's just one proposal.
Thanks. Okay. Yeah, I mean, I know people worked out some matrix models, which mean most where the degrees of freedom are just matrices, like some SUM matrix model, and they have some gas for that function in those cases. I think for SU4, it's known to take some for this 4, something like that. So there are some examples in the literature. I don't know, but I don't have them on the top of my heart.
Okay,
Top
thanks.
of my head. Okay, so since this is getting comment on vortices. Okay, so try to highlight so far everything which was systematic and everything that follows from general EFT principles. Okay, that's fine. But I want to say there is quite some literature, or quite few papers, at least from me, about vortices in effective field theory and their role. So I want to say something about it. But I will not give details because I think there are already 2 recorded talks about that, so in the Bootstrap channel. So it's too much. So one curious feature, so let's go back to the U1 EFT. So now you have just one Goldstone boson. So just for, just to remind you, the action in this case is C1 d chi cube. And this EFT has a curious feature that it has an emergent 1-4 symmetry. Of course, it's a typical case with massless Goldstones, where G mu nu is just the winding of the Goldstone boson. Of course, this is known since ages, it's just conservation of vorticity. But now in modern language, if you find a symmetry, you should expect it to be broken. I mean, either it should be an exact symmetry of the theory, but I think there are many arguments why you shouldn't have continuous U1 1-4 symmetries in a theory. I think essentially only free theories have them, but people who are more experienced can tell me. So therefore, you should expect there should be degrees of freedom that break this symmetry. And so expect, and since you don't have these degrees of freedom in the effective field theory, you don't have operators that break this symmetry in a controlled way, you should expect something else. Okay, so these are all fancy words, but all I'm saying is that you should expect that the theory admits vortices, and this actually is known very well from fluid dynamics. Okay. So vortices are just location where the velocity of the fluid, just roughly the gradient of the fluctuation, becomes singular. So why is it an assumption, if this is a solution of the equation of motion, why is it an assumption, this x alpha are the vortex cores? So why is it an assumption that they are in effective field theory? Well, it's an assumption because if you write their energy, the energy of a single vortex, this is roughly given, it's very intuitive, integral over the mass, v square. And now if you perform that integral over that solution, you find it is mu logarithm of, some IR cutoff and some UV cutoff. So the picture you should have in mind is that your fluid is winding around a point here, and I'm making this point thick with some radius A. So you see, it could in principle happen that the radius of the vortex goes to 0, then vortices are infinitely energy, and in this solution are disallowed. Here instead, I'm saying in effective field theory, I cannot know what's the size of the vortex that I'm cutting off at A, and by dimensional analysis, A will be 1 over mu. So you see, you predict that the vortex has an energy mu log r mu, or square root of q log q if you want, with a calculable coefficient. So, so then it's natural to include them in the effective field theory. Now, you may say, how should I include this solution in the effective field theory? Well, I should give dynamics to the cores. But then why should I do it? They're heavy. I cannot trust them anyhow. But there is a basic feature of vortices, which is that they carry large angular momentum. So to understand this, it's better to dualize the scalar. So this is something I think everybody knows, but let me just write it down. So there is a duality between a shift invariant scalar and a gauge field, just the same number of degrees of freedom. And the duality matches the currents on the two sides. So on the one side, the current is a U1 current. On the other side, the current is a topological current, where this is the field strength. And J mu nu on the dual side is just the field strength, roughly, and the conservation, and therefore the non-conservation due to the vortices of the field strengths is just the Gauss law. So vortices are charged particles. So the conclusion is that vortices are charged particles. So let's do just in static frame. And then why vortices carry large angular momentum? Well, the angular momentum of a particle is given by the standard electrodynamics formula. So J, the angular momentum, is roughly the integral of the electric field wedged the magnetic field, as you know from electrodynamics. But the magnetic field, because of this, is huge. The magnetic field is Q. So even a tiny electric field sourced by a tiny vortex can source a large angular momentum. So each vortex carries, you can do a calculation, angular momentum Q alpha. So this means that if you start considering states with large angular momentum, they might become convenient to include in their theory. So these people already heard many times, but so and then I'll stop. Going slow. So just let me mention two applications, and then maybe we can conclude for today. So a generic feature of the effective field theory described is to have vortices. And then the point is that you can use them to describe large A ground states. And turns out you can arrive to cover the whole regime between square root of Q, which is where your effective field theory should have broken, to Q square. And actually an interesting question here. So we find that parametrically, when you approach this side, you start to agree with the expectation from the multi-trace operators that Peter discussed. An interesting question if you can start from the large spin toy model that Peter discussed yesterday and recover the condensation to a superfluid in some sense. And Another application of vortices is this large Q Chern-Simons theory. So large Q in Chern-Simons theory. So to understand this, it's better to have a toy model in the head. So imagine this theory, a Chern-Simons field coupled to a gauge field, to a fermion. Here the equation of motion for k4 pi b. So here the charge is b, it's the dual charge, to be equal to the charge density of the fermions. Huh? One flavor for now. One flavor large K.
Okay, sorry. The question was that how many flavor Lambert in this area, and he answered just one for me.
So I'm taking just one flavor, and the U1 charge is the topological charge of the gauge field. And turns out that, okay, so this implies that there are K fields, so the fermions organized in Landau levels in the presence of the U1 charge, and there are K field Landau levels, minus K plus 1 holes. So if you imagine your Landau levels, you have the first Landau level, the second Landau level, until the kth Landau level. Here you will have a finite number of holes. So a state with k field Landau levels, a magnetic field, it's known from a paper of Witt and Wilczek and others to be a superfluid. So you can apply your effective field theory. But then you have to still explain these holes. And these holes turns out to naturally coincide to vortices in the FT. So anyhow, if you're not familiar with any of this story, which is okay, the bottom line is that in Chern-Simons theory, the ground state, even the ground state carries vortices, but the vortices are very quantum delocalized, so they don't lead, eventually they combine such that total angular momentum is 0, but they lead to new excitations on top of the ground state. And this is a generic feature of all Chern-Simons theories. Okay, and it can be described in EFT. So, when I'm supposed to finish, like in 5 minutes, or? Okay. Yeah. Yes, I'm just trying to think what I think I covered. I wanted to do more, but I think I did already a lot, and I think people are tired. So I don't know. Yeah, I wanted to say about something Monte Carlo. I think that's lighter. So, okay, so we did. Okay, let's stop calculation. Just do pictures. And when I say let's stop calculation, it means that José can do the calculations for me here. And actually, okay, so. Okay, so
this was only in 3 dimensions.
So
Because experimental, it's more interesting.
yes, so I mean the effective field I described it also in D dimension. The comments on vortices are in 3 dimension, all in 3 dimension.
And in 2D, is there something interesting or it's too boring?
So 2D, I think the problem is that it's very constrained. So, okay, my understanding, the best understood examples in 2D are rational theories. You have enhanced symmetries. And it's very hard to include them in the FT. And furthermore, I think you only have a finite number of primaries typically. Like the charge, you cannot make it arbitrarily large if you stick to primaries of the chiral algebra. So my understanding is that 2D, this formula is, essentially doesn't capture anyhow the. I think it's hard to make this formula is compatible with the Sukavala theorem, to be very technical about the stress tensor.
It's too fancy. So if I have just an operator with lots of charge, and I
But it's
consider
typically
two of
going to be a
them,
descendant of some true primary, right? Of the chiral algebra, of the full extended algebra, right? So typically, rational CFTs have only a finite number of primaries.
Right, but it's true that we don't have any concrete examples, but that might make it more interesting to figure out the expectations from effective field theory for a generic theory that does not have.
I mean, you can write the U1
An enhanced
effective field
chiral
theory. You can write a U1 effective field theory for a theory which has not enhanced scalar algebra. It works. It's very funny instead that somehow many things simplifies. People, Zohar, Sridip, Mark, and Avia studied this, and it's not inconsistent.
I mean, you don't have Goldstone bosons, but
I mean,
maybe
it's not a big problem, right? Even here at final one, you don't have Goldstone bosons. It's just when you have a light excitation which is lighter than the other. Like here in BKT, it happens. I don't think that's a big caveat. Yeah, it's hard to figure out concrete example. That's the only thing I have to say. Okay, Monte Carlo. Okay, so I haven't given really many references just because I think most of what I said is in the reviews, but here I want to give credit because these are very hard calculations. So, okay, I'm never going to write it right. Chandrasekhar. Orlando, 2017. And okay, the last paper. Oliveira. Okay. So the state of the art, I think, so this is the first paper I did Monte Carlo, and the state of the art, I think it's, for what I say today, is in this second paper. And let me highlight José and Julio, who actually did the simulations. So the idea is that Monte Carlo can measure for you scaling dimensions and OP coefficients, but it's very hard to do it at large charge. So these people had to come out with a very smart algorithm, this warm algorithm. And currently, people measure delta Q up to charge 19. And you find a curve like this, and a best fit curve. Sorry, in the O2 model. Thank you. In the O2 model. And so people fitted this formula, and here this is, and they found from best fit these values. Okay, so overall, what the fit, so the fit, I should say, I think this was a nice best in this last paper, is not performed for all charges, because you might have, so one natural question did 1 over Q expansion. When does it start working? So now we have numerical data. Let's compare. And turns out that the fit stabilizes only from Q equal 4 on, roughly. So which tells you Q equal 4, 5 is already pretty large. But in fact, even if you extrapolate the best fit done with Q equal 4 to Q equal 19, I think Jose can correct me, I think that already at Q equal 1, the error is like 2% or something. So it works remarkably well. I'll now comment for a moment on this, but another caveat of this fit is that the precision is it's hard to get high precision, and therefore the Q to the 0 term, which is this Casimir energy, we couldn't get it reliably. But you can measure these two coefficients. So one explanation why maybe it works so well also at Q equal 1 is that this series, I said, should be an asymptotic series. And asymptotic series have optimal truncations, and it's possible the optimal truncation kind of coincides with the first two terms. But of course, this is really, at large M, people try to make this precise.
But, are you going to comment that I think the first paper did simulations not in the cylinder geometry, but in the torus geometry? What about your paper? We did all, no, so we're only doing so we're doing torus geometry. So we're doing two-point functions. So we're taking the torus to be very large, so that finite volume effects are not relevant. We're really measuring the two-point function. So they also measured the energy on the torus, and wasn't going to comment on it. So in fact, I don't think in their paper they measured the scaling dimension of the operator. I think they measured the energy on the torus. No, I think they did both. In this paper, they did both. I think they measured the energy on the torus, which is also supposed to have a Q to the 3 alpha term with coefficient that is related to this alpha 1, and they found some agreement. But they also measured scaling dimension up to Q equal 12. I think so. I mean, they just said, right? So that's over here. Yes.
Yes. So okay. So maybe. So I think what Jose is saying is that the way they did the simulation, it's not actually the strategy we use, but is that they did OQ 0, or dagger Q at opposite side on the torus, so on the torus. And this is predicted to go like 1 over L to the 2 delta Q times a function that we don't know. And then they increase the size of the torus. And from this, they extracted the scale dimension. So that's true. So maybe that's what you're referring to. Yeah. So actually, since there was this question, actually, there is a natural way to improve this, is to put the two operators a bit closer and see if finite volume effects are important. And that's what I think Joseph figured out very nicely how to do. The other part that we measured are OPs. I didn't have time to talk about today about them, but so I'll just give you the prediction. The large charge can only predict for you. 1 minute. Let's do this. Okay, so sorry guys, you're right. So there is a prediction for the OP coefficient of free large charge operators. A function of some times some number, which I think is roughly 0.98. So in a paper of mine, there is this prediction at large charge for an OP coefficient. And we were interested in checking it because this prediction depends on the same Wilson coefficient alpha 1 appearing there. So this would be correlate two different observable, and this would give more evidence about DFT. I mean, that formula tells you there is a 1 over Q expansion, but it doesn't yet correlate that with another observable. So unfortunately, here you can only do Q equal 4 and try to fit. So you can take with a grain of salt these results, but okay, that's what is very hard. So we did it anyhow, and Jose did it actually. And the main point is actually this alpha 1 turns out to be like something between 0.28 and 0.44. Before it was like 0.34. Of course, the error here is huge because we are fitting with 4 points, but it's compatible with the measure before. So we believe that with all the grain of salt, this provides strong evidence for the validity of the effective field theory. And okay, that's all I had to say. Sorry.
Any question? We can, of course, continue asking questions during coffee break.
Sorry, Gabriel, just one quick logical step. So you mentioned yesterday that for small q, everything comes from the vacuum properties, and then large q, you find a new saddle.
Yes.
But here you're presenting plots for small q, arguing that the same...
I mean, so that was in the weak coupling, you need epsilon q to be large, right? In the weak coupling, I think you found that this large charge expansion, maybe I didn't say it, was valid when epsilon q was kind of larger than 1. Really, that's what you found. So you extrapolate epsilon to 1. This suggests that maybe the extrapolation of these formulas to small q, it works. Here we could test it because up to q equal 19. That formula we couldn't, so we just hope to get lucky because that's very hard to do simulations.
Very good. So let's thank Gabriel. And It's a pleasure to have Alexandre continue on the theme of yesterday's lecture.
Thank you. It's good to see everyone, and it's good to talk here. So thanks for the organizers for the opportunity. So today I would like to share some ongoing computations we are doing with David and Pedro on the physics of complex spin and light ray operators in planar n=4 sparing Mills at weak coupling. So let me start with some motivation. So Simon taught us that out of a 4-point function, O1, O2, O3, O4 in CFT, we can construct functions C of the dependent on the external operators and functions of delta and S, so that the singularities in delta, they provide continuation in spin of the CFT data. Now, a year or so later, Peter and David, they suggested that we should interpret these singularities in delta as light ray operators. However, both of Simon's construction of the continuation of the data, as well as Peter and David's construction of the light rays, they make explicit reference to the external operators that we use to construct these objects. However, I think there's the expectation that both the trajectories as well as the light ray operators, they exist in a way that's independent of the 4-point functions we use to construct them. Much like local operators exist in a way that's independent of these in which they flow. So this idea we call light ray universality. In the sense same that local operators are universal, light rays should also be. Now, we would like to investigate this type of ideas by trying to construct explicit forms for these light rays in this gauge theory without making reference to 4-point functions. So the question is to construct light rays and moreover, we would like to, in this construction, try to see if there are some general lessons that we can extrapolate from this particular theory to the general setup. Now, the second motivation is conformal Regge theory. So a few years ago, Simon and Joshua, Sandor, they provided a convergent expansion for 4-point functions in CFT in the Regge sheet. And this convergent expansion, to make use of it, requires complete understanding or complete control of the left half plane singularities, left half plane in spin, the singularities in the left half plane of all the continuation of the data. However, also a few years ago, Joan was giving some lectures on Regge theory in California in the Bootstrap meeting, and he made us aware that there might be dragons in the left half plane. So we would like to investigate these analytics in the left half plane in this theory to see whether there are indeed dragons or there perhaps some extra simplicity. Now, this analyticity has been explored in other contexts in the past, but their analysis is usually resumed to either leading singularities or to some special lowest trajectories that admit extra simplicity. So I'd like to explore some more general trajectories in this theory where we have lots of control. Now, the third point is related to what Peter was describing yesterday, which is this feature that in higher twist sectors in CFT, there is a growth of the number of primaries in spin. So, for example, in the gauge theory, let's consider some operators that are single traces of the form d to the s times z cubed to illustrate this problem. They should have some permutations inside the trace to make this a primary. If you count these operators, it's a very fun combinatorics problem to count them. You find that there are two integer part of s over 6 plus 1 primaries for even spin. And I've plotted the one loop twists as a function of spin here in this plot. So today I'm using a conventional orientation of the axis. You see that in this theory it's very clear that these many primary operators, they neatly organize into some trajectories. And the number of trajectories grows in spin in steps of 6, as Peter mentioned yesterday. Now, this growth in spin leads to a naive puzzle, which is that if you assume that these trajectories indeed continue in spin, then if you expect that they continue nicely to lower spin, then you might be puzzled, because at any given spin, you would expect to encounter an infinite number of trajectories. And our expectation is that the trajectories, they should contribute in CFT correlators at even spin. So for example, you would expect to see in some OP an infinite number of contributions at spin 6. And that's of course not what we observe. We only observe at a given integer spin the contribution of the local operators. So the question that was discussed yesterday was on the resolution of this apparent paradox. So here in this plot, I'm showing you the square of the structure constants with some particular external operators for this trajectory that I highlighted in red here, which starts at spin 6. So it turns out to be a sequence of exponentially decaying numbers. And the resolution to this apparent paradox, as we understood in our last work, is that as you continue this trajectory in spin to small values, instead of continuing to blow exponentially, after you pass the last physical operator, what happens is that this trajectory actually turns around and places simple zeros at the position of the even integers, so that in the end, what happens is that this trajectory simply decouple precisely when they would contribute to CFT correlators. So this resolves the puzzle, and we call these zeros decoupling zeros. So let me just briefly mention how we managed to make these conclusions last time. So what we did was to show that there exists some sequence of polynomials pi, which are polynomials in spin, with the property that they converge to the unique continuation of the square of the structure constants that satisfies the correct Reggie behavior at a large spin for all s in the right half plane. And moreover, these polynomials, they are constructed entirely in terms of the CFT data, which we know very well in this theory because of integrability of the planar dynamics. So from the integrability, we can construct these polynomials, and from this, we can reconstruct this continuation of C and just simply observe the zeros. So today, I would also like to give some different perspectives on this issue. And the fourth motivation is integrability in itself. or more precisely, where we can develop an integrability framework to compute matrix elements of light ray operators in this theory. Now, this is interesting in its own right, because the physics of this object is very interesting in the gauge theory. But here I want to give a motivation that's a bit more geared toward general CFTs, which is that developing such integrability framework could provide us with data to check proposals for the OPE of general light rays. Now, there is some understanding, thanks to the works of Sean Han and Murat, Peter, David, and Sasha, on the OPE of the light transform of local operators. But an understanding of the OPE of general light rays in CFT is still lacking, and integrability could provide some help in that. Okay, but I'll actually not talk about this at all today. Instead, I'll try to focus on the first 3 points, and that's it. So maybe let's start. So I'll start from the third point and then go up. So the first point I want to discuss is what we call spectroscopy. So let's consider the second trajectory that we highlighted in red in the plot that I just erased. So let's define the spin for each of the NF operator in this trajectory, which is 2 n minus 1 plus 6. So the first operator has spin 6, the second one has spin 8, and so on. And let's define a generating function, f of t, where we sum over all operators in the trajectory, n goes from 1 to infinity. We construct a power series, t to the n minus 1, where the coefficients, f of s, and s you should be understanding as a function of n through this, is equal to the inverse of the square of the structure constant times some gamma functions. So what are we doing here? We are essentially removing from the structure constants the leading large spin asymptotics. So the claim is that if you perform some large spin analysis of this summand from, say, light cone Bootstrap, you'll find that f of s, with this factor removed, so I mean with this factor included, is polynomially bounded because we remove the leading exponentials. Now, what does it mean that f of s is polynomially bounded? It means that this power series now has finite radius of convergence. This means that f of t converges for t in the unit disk. You can see that from a ratio test, because the ratio of the f's will converge to 1 due to polynomial boundedness, while t smaller than 1. So this is by construction. We chose f of s so that this holds. However, much more is true, it turns out. It turns out that the two following properties hold. F of t is actually analytic, not on the unit disk, but is analytic in the full complex plane minus the cut from 1 to infinity. And moreover, f of t is polynomially bounded. At infinity, asymptotically. to see this, let's introduce this uniformizing variable rho of t, which is square root of 1 minus t minus 1 divided by square root of 1 minus t plus 1. This variable maps the full complex plane minus the cut to the unit disk. It maps 1 to minus 1, and it maps infinity to 1. The upper and lower parts of the cut correspond to the boundary. And we can write now f of t as a power series in rho. It's the form rho to the n, Cn, where Cn is determined from the data. So it's just a change of variables from this power series. So essentially, Cn is given by f of s, some combination of f of s. And so the Cn's are known, and then you can just verify numerically in this theory that everywhere inside the unit disk in rho, you find that this power series converges really well. And moreover, you can also compute the discontinuity around that cut from this numerical construction. So you find, for example, that the discontinuity of f in the t cut is simply given by f of rho minus f of 1 over rho at absolute value of rho equal to 1. So again, you can compute this from data. You can find that this converges everywhere in the rho disk, and you can efficiently compute its continuity around this cut from this formal series in the uniformizing variable. Now, the way I'm explaining this so far is simply the statement that we checked that f of rho converges in this region. But you can kind of understand that these properties are sort of a consequence of the analyticity in spin of these objects. This will be made more explicit. So now, what does it mean that we have analyticity in the cut plane with polynomial boundedness? It means that we can write dispersion relations for the coefficients in the expansion of f around the origin, or namely the structure constants inverse. So we can just write some contour formula that extracts the Taylor coefficients in that generating function, and then blow the contour up to write the following expression. We learned that f of s is given by an integral along the cut of the discontinuity divided by t to 1/2 s minus 6 plus 1. So let me just emphasize again that this formula is correct, and you can just check it to arbitrary precision by plugging its continuity computed in this way here, and performing these integrals for the even integers, and reproducing from this expression the data you know from the CFT. Yes, yes. I think.
Can you repeat that?
So João is asking, what do I mean by I know the data? By I know the data, I mean that I can compute the CFT data using integrability up to, say, spin 1000, and then I can see very good convergence of these formulas as I consider more and more terms in the summands. So what did we, so let me emphasize that this formula converges for large enough S because f is polynomially bounded. And then I can define f of s everywhere else by continuation in spin. So what we are gaining by writing dispersion relation is that this formula is now manifestly analytic in spin. And more than that is true, the spin enters in a very simple form through the exponent here, which means that I can, the only way that this object can have singularities in spin is if there are divergences in this integral due to the large T asymptotics of the integrand. So what we are learning is that we can trade the analysis of singularities in S by asymptotics of disk of big F. So due to this, we are invited to analyze the asymptotics of the discontinuity, which I emphasize we can compute very well numerically. And what we find by, for example, fitting this discontinuity at large T, we find that this admits an asymptotic expansion of the form, the first three terms in the asymptotic expansion are some pure powers, T to the n, so it decays, plus some little o, something that decays faster than T to the minus 3. So we can compute this to very high precision. So we can determine that this is really an integer, and we can compute this residue very well from the data. Now, what does this asymptotic mean? We plug it back in the dispersion relation to find that f of s is 2 a1 over t, sorry, a1 over s minus 4 plus a2 s minus 2 plus a3 over s plus some reminder that is analytic or holomorphic in the right half plane. Now you observe that from the asymptotics of the generating function, we learned that f of s has poles at the even integers, which in turn correspond to zeros of the structure constants. So in this way, we recover the decoupling zeros that we learned before from the polynomial interpolation methods. However, more is true. There is extra insight to be gained from this analysis, which is that we could try to understand further asymptotics of this generating function, which would correspond to singularities in the left half plane in spin. So for example, suppose that there is a term in the asymptotics of the discontinuity of the form t to some s star minus 6 over 2 times some logarithmic behavior, t to the minus 1/2, for example. This would in turn correspond to singularities in f of s, which are of square root type around s star. So you can imagine learning about the left half plane by doing some precision analysis of these types of objects, and in this way reconstruct step by step f of s everywhere. Now, I'll move on to the second topic I want to discuss, and I'll not tell you about the result of this left half plane analysis. Well, I'm going to talk about the left half plane, but from a different perspective now. So I'm going to shift gears a bit. But the result will be that this idea actually doesn't work too well in practice, and this will be clear, and why will become clear soon. So let me maybe summarize here. So the idea is that we construct some kind of inverse amplitude through this generating function, which admits a dispersion relation that provides analytic continuation in spin of the CFT data, and for which we can exchange the analysis of singularities in S of the inverse amplitude by the asymptotics of the generating function, which can be computed very well from the CFT data. And in this way, we can recover these decoupling zeros. So the next thing I want to say is that we developed some novel integrability technology that allow us to compute the anomalous dimensions or the conformal dimensions of these higher twist operators everywhere in the complex plane. which is something that we couldn't do before in this case where there were infinitely many Regge trajectories.
We need one of those cubes that we can throw. So here the expectation is that you just keep having poles at s plus 2, s plus 4. Is that what you expect, or you just don't know, or what's the...
So these are all the singularities of the inverse amplitude in the right half plane.
Right, but if you
If you move further, then, for example, the expectation is that you could perhaps have some asymptotics of this type, which is...
But this you're just saying maybe, or you have some evidence for this?
I'll get there, I'll get there.
Okay, you think there are worse things than poles?
I mean, you think there are worse things than poles.
Dragons represent ignorance, I don't know.
Okay. So, yeah. So as I was saying, we developed some novel integrability technology that allow us to compute anomalous dimensions or conformal dimensions of all these higher trajectories in the full complex plane. Now, I don't want to describe what this integrability machinery is because I don't think that's the interest of most people here, and it's also quite complicated. I just want to share the result and ask you to trust me that this new machinery is very efficient and it has been very well tested in regimes in which other methods are available. So I just want to share the result from this analysis, which is that these infinite Regge trajectories, as you move to the left half plane, they form a Riemann surface with three components, three connected components. The first component corresponds to the continuation of the lowest twist trajectory, which in this theory has some enhanced symmetry and therefore lives on its own. The second connected component corresponds to all odd trajectories. And the third component corresponds to all other even trajectories. Say again? Odd spin. So odd and even spin trajectories, they have different quantum numbers, and therefore they kind of live in separate spaces. But otherwise, the picture in the complex spin plane is as follows. So in the right half plane, there is nothing interesting besides these decoupling zeros. However, in the left half plane in spin, we find for the even or odd trajectories that there is some kind of triangle here whose tip is around -2, inside of which there is a proliferation of branch cuts or branch points which mix all of the Regge trajectories. So each of these branch points is quadratic, meaning that if you go around twice, you go back to yourself, and they also mix only two Regge trajectories at a time. Now, using this integrability machinery, we can reconstruct this Riemann surface numerically and just plot all of these sheets connecting and going around. And in particular, something that's very fun that you can do is that you can start, say, from the second trajectory in the right half plane at some integer spin, deform away from that point adiabatically towards the left half plane, perform some monodromies in this region, and then adiabatically move back to the right half plane and reproduce the CFT date of, say, the seventh trajectory. So I think the conclusion would be that there are indeed dragons. There is no unexpected simplicity in this structure, which perhaps is something that we would expect in general CFT, that up to global symmetries, all trajectories should mix in principle. But it's nice to check concretely in this example in which we have analytic control to verify that indeed there is no unexpected simplicity. Sorry, how long have I been talking to? So I talked for 30 minutes, right? Okay. Any questions? I'm going a bit fast. So the question was, why is this the lowest trajectory separate? I don't have a space-time explanation for why it's separate. I have an integrability explanation, which is that in the worksheet description of this trajectory, there is some extra parity symmetry that's protected only for this lowest trajectory. It's kind of a more symmetrical configuration, and it therefore has some special quantum numbers which say it cannot mix with the other trajectories. So
so when you say that you see all these branch points and you can move around, can you specify what kind of at what level you're doing the calculation? Is it something like finite lambda planar theory or something else?
no, it's a weak coupling. So
Weak coupling.
one loop.
But then if it's one loop, then you shouldn't see that these branch points are...
Poles?
Yeah, you see that they are poles,
No,
really?
no. These are really branch points at one loop. And the reason this is possible is because all of these higher twist trajectories at weak coupling, they have the same conformal dimension. So they already sit on
right.
top of each other
Yeah,
to lead in
okay.
order, and therefore they can mix right away.
I see.
They are not like trajectories that intersect at a point.
But you don't see any poles, so you don't see...
We do see poles, I didn't mention them. Of course, there are poles here, for example, at the even integer in the left half plane, which have the usual interpretation of BFKL horizontal trajectories that intersect these diagonal trajectories.
Okay, thanks.
Yeah. So yeah, as Peter has mentioned, there are also poles that are something that's more standard, perhaps. So there's lots of things to explore here, but okay. So at finite coupling, at finite coupling, the expectation no, lower twist. I'm not sure. I'm not sure. I expect that in perturbation theory they should not mix, and I guess then therefore they should not mix ever. But yeah. They should mix? Yeah, in perturbation theory there is a symmetry. I don't know what's the fate of the symmetry at finite coupling. That's the point.
All right, I was saying that I think they should mix, and unless it's protected.
No, but yeah, the whole point is that there is some extra symmetry, which I don't know how to describe in space-time, but in the worksheet is essentially parity on the worksheet that tells you that these lowest trajectory shouldn't mix. I don't know what happens at finite coupling or finite n or what. But, well. Okay, so next point. Here. So the next point I want to discuss is the construction of light rays in this theory. So let us focus on these twist tree trajectories, and as we go along, I'll make some comments on how this generalizes to higher twist. So the picture we'll be considering is that we insert this light ray we want to construct at past null infinity in the Minkowski, And the ansatz is that this object is made of 3 partons. So the proposal is that this light ray is given by an integral of 3 partons whose position along the light ray is given by alpha I. And it's a single trace operator, because we're continuing single trace families, of z-field insertions at position alpha 1, alpha 2, and alpha 3. Again, some wave function psi of the coordinates of the partons. Now, the first thing to understand is what are the constraints on these light ray operators that arise in the free theory already. So we require that these transform as primaries inserted in the past null infinity in free theory first. So primaries inserted at the past null infinity, they are annihilated by the momentum generator, which in turn implies that psi of alpha I is translation invariant. So this is P on O equals 0. Now the second condition is that this should be an eigenstate of the dilatation operator in the free theory, which in turn provides an homogeneity condition on this wave function, which in this case is homogeneity of degree -2 minus S psi of I. So this is dO. And then there are some discrete symmetries. Dilatation operator diagonalizing the light ray. Yeah. This is O times lambda to the 1 minus S, or L delta of O. This is no, S of O. Yeah. Okay. And then there are discrete symmetries. So one thing that Peter and David showed when they discussed the light rays was that the light transform of even spin operators, they were eigenstates of applying CPT operator and then performing Hermitian conjugation. So, sorry. This is light transform of an operator of even spin, local. This, they showed, is equal to this. Now, the proposal is that this eigenstate condition remains true at complex spin. So the light ray operators should be invariant under acting with CPT and performing Hermitian conjugation. This implies that the wave function is invariant under inverting the position of the partons. And the fourth condition, at leading order, is the discrete symmetry associated with the fact that we have a trace of 3 identical fields, which means that the wave functions should be invariant under cyclic permutations. Okay. Now, to explore these leading order constraints, let's introduce some useful variables. So first, introduce some center of mass variable, which is the sum of the alphas. And then we introduce some radial coordinates by saying that alpha 1 minus alpha 2 is r cosine of theta, and alpha 2 minus alpha 3 is r cosine of theta minus 2 pi over 3. And then from these two conditions, automatically you get that alpha 3 minus alpha 1 is r cosine of theta minus 4 pi over 3. And these variables are very nice for the following reason. The first constraint essentially tells you that psi doesn't depend on the center of mass variable, and therefore it's a distribution that depends only on r and theta. Now, the second condition implies some homogeneity condition on R, and homogeneous distributions in R of this degree, they are necessarily of the form g of theta times R to minus 2 plus s, where g of theta is some distribution on the circle that is left to be determined. Let me here make a comment about what happens in the higher twist operators, where we have more particles inserted among the light ray. Then we would have more variables here, and using these two first properties, we would be left with determining a distribution on L minus 3. Now, 3 and 4 provide some discrete symmetries of this wave function g, L minus 2. Now, 3 implies that g of theta, so this is 3, is equal to g of theta plus pi, while 4 implies that g of theta is g of theta plus 2 pi over 3. And combining these two conditions, you find that g of theta is invariant under shift by pi over 3. So we have this Z6 cyclic symmetry of the wave function. This is the worst Z6 ever. Okay, now so far all that we discussed is kinematics. Now we need to input some dynamics. So to discuss the dynamics, let's make me some two obvious comments that sound a bit silly, but soon they will not be silly, which is that first, there is the first order differential operator, P, whose light ray operator is an eigenstate of. Now, because of the second condition, there is also a second order differential operator, the quadratic Casimir, that also is diagonalized by the light ray with some eigenvalue, which is a simple function of S. Now, this is general. Now, because of the integrability of the planar dynamics in this theory, there are actually higher order differential operators that continue this sequence that also should whose O should also be an eigenstate of. So what I'm saying is that there exists a third order differential operator, D3, whose action on O should be Q of O. So these higher order differential operators, they essentially probe higher integrable charges of these objects. Now, this is a very standard story in the case of local operators. And this family of higher order differential operators, they can be constructed with a method called algebraic Abiti ansatz. And there is in fact a generating function for these operators, which is the transfer matrix. What we are proposing here is simply that this story that holds for local operators remains true for the non-local light rays. They are also eigenstates of the transfer matrix. So the point is that this object it's known how to construct, and we are now proposing that this is true for light rays. And we'll see what are the consequences of this assumption. But you should think that this extra differential operator is a differential equation on g of theta. So this should fix g of theta, provided we understand boundary conditions. Now, to analyze this differential operator, it turns out it's very useful to go to Fourier space, because things simplify dramatically there. So we express g of theta as some sum over n of Fourier coefficients an times e to the I 6n theta. Now, only Fourier modes with frequencies multiple of 6 appear in this decomposition, precisely because of the discrete symmetries of the problem. This is to be understood in the sense of distribution. So this expansion doesn't converge pointwise, but if you think of it inside of integrated object, it makes sense. Now, once you write this Fourier decomposition, this differential equation takes a very simple form. It reduces to a three terms recursion relation. So we find that this differential equation becomes C of n and s, a n, plus C n plus 1, n and s, a n plus 1, plus C n plus 2, n and s, a n plus 2, q a n plus 1. It was crucial here to use these discrete symmetries. Otherwise, this would be a 13 terms recursion relation. So because of discrete symmetries, we reduced to 3-term recursion. And the C coefficients of the recursion are some simple polynomials in n and s. So to understand how to fix the light ray operator completely and solve this recursion relation, we need to understand what boundary conditions to impose. So we are invited to analyze this recursion relation at large n, so at large Fourier modes. So for that, we assume an asymptotic expansion for an, which is a form of our series, so it's n to the alpha times 1 plus some sum of some c, well, d I n over I. And we plug this expansion in the recursion relation and analyze. And what we find is that alpha must be either -1 or s. So a general solution would be a linear combination of these solutions that either decay in Fourier space as 1 over n, or they grow as n to the s. So let's suppose that we consider this solution that at plus infinity, so at here is n, here is the absolute value of an. Suppose that plus infinity, we consider the solution that decays as 1 over n. And then we use the recursion relation to move down towards small values of n. Generically, the solution will be complicated in the middle. But then at minus infinity, it must once again be a linear combination of those two solutions with different asymptotics. So here it's a mix of growing and decaying. So there's this connection problem of determining what's the combination at minus infinity given some asymptotics, pure asymptotics at plus infinity. The precise combination between these two solutions will be a function of q, the parameter q, and s in the recursion relation. Now here's a proposal. The proposal is that the light ray operators that continue the CFT data appropriately, or they continue the light transforms, are precisely the pure solutions with 1 over n asymptotics in Fourier space. Now, as I just discussed, for generic values of q and s, these solutions do not exist. Solutions that are 1 over n in one side will be a mix in the other side. However, at fixed s, you might imagine fine-tuning q so that the growing part of this left asymptotics vanishes, and you are left with a pure decaying solution. So the claim is that the existence of these pure solutions is a quantization condition for q. Now let me provide some intuition for this proposal, which is that we know that the asymptotics of the Fourier expansion kind of control morally the smoothness condition of the functions. And by saying that we have pure decaying Fourier modes, we are essentially saying that we do not allow for the light ray operators to be too singular. And this should translate into some analyticity or smoothness properties of the CFT correlators in which they are inserted. So this is the sense in which perhaps this is some general lesson. So, of course, I'm telling about this proposal because it's correct, otherwise I'll not be talking about it. And how do we know it's correct? Well, first it provides a quantization condition for Q, and in particular a function, expression for Q analytically dependent on S, which we can compare with what we obtain by, for example, using these polynomial interpolations to compute the analytic continuation of Q. And so we see that this Q quantization matches what's known from previous, from alternative methods. The second thing is that we can just compute these pure 1 over n solutions for the quantized values of Q and act with the dilatation operator on these objects and recover the anomalous dimensions we computed using integrability. And we verify that these operators, they have the correct one-loop dimensions or energies. And finally, with the explicit expressions for these pure 1 over n solutions, we can compute their structure constants following what Peter discussed yesterday, for example, and we can verify that these 1 over n solutions, they reproduce the decoupling zeros that we've been discussing. So this clearly works. You might wonder whether this solution is unique. So what happened, for example, if you consider instead pure growing asymptotics? And what you find is that the correlation functions in CFT in which you insert these light array operators with growing Fourier modes, they are well defined in the sense you can compute them, but they are sick in the sense that in the right half plane in spin, at large spin, they have they blow up exponentially, and so they do not respect the properties we expect from Regge theory. So they do not provide good analytic continuations. Okay, I'll stop here.
Okay, we have lots of time for questions. So can I pass it to Peter?
So I didn't quite get it. Can you actually solve this in some form, this recursion relation, or is this some sort of numerical checks when you?
So your question if you can solve it analytically?
Well, for example, you say that it gives the correct quantization condition of Q, so you need some sort of solution of a connection problem. Do you have an analytic solution, or is it some sort of numerical?
No, it's a numerical computation of the solution. So what we do is that, well, there are many ways of seeing it. So suppose you know Q. Suppose you know the quantized value of Q. Then you can just plug some asymptotic expansion that decays as 1 over n. And this will provide a good approximation to the solution at large n, say at positive n. You can then use the recursion relation to move away to finite values of n, and in this way reconstruct the Fourier modes at finite n. And then from there you can just, you have essentially the Fourier decomposition numerically for these operators, and you can start computing physics. Now suppose you don't know Q, and you also want to determine those. Then one way of thinking is that this recursion relation is kind of a discretized Schrödinger operator. You can think of this as a discretized Laplacian, whose Q plays the role of energy, and we are looking for solutions to this quantum mechanics problem which are bound states because they decay at 1 over n. So you can just look for the eigenstates of this Schrödinger operator, and those precisely match the Q energies that you need to consider.
I see. So you basically kind of truncate on both sides and
yeah, because they're decaying.
Okay, thanks.
Naive question. So, can there be extra constraints on these wave functions from the limits of colliding alphas, or this physics is not constrained by anything?
Colliding alphas. What are alphas?
I mean, when two of the partons get very close to each other, is there some extra constraint from OPE, or I mean?
So, essentially, the asymptotics of the Fourier modes, they are a probe of the smoothness around the singular points in position space. So singularities in position space of a given degree, they correspond to certain asymptotic growth of Fourier modes. One way of thinking of this is like, for example, suppose that in position space there are S derivatives of delta function singularities. This would correspond to n growing polynomial as n to the s. Saying that it decays as 1 over n means that the singularities in position space are essentially log singularities at most, morally.
More questions?
So just to make sure I understand, this was is this for any coupling or what?
This analysis at weak coupling.
This is all still at weak coupling?
Yeah.
Thank you.
So maybe, so would this boundary condition change as you tweak the coupling?
I think the expectation is that no, that perturbatively this should remain true.
But you said
Well-
somewhat associated to logarithmic singularity, which sounds very perturbative.
But well, higher order perturbation theories are still perturbative, right? But let me point out that well, let me not point out anything.
Any other questions? If not, let's thank Alexandra. So let me remind people, some people are new,